Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. The Strait of Hormuz is in the news. The big question in everyone's mind is what vessels are in transit through the strait. Here is a quick exercise to establish a dashboard that can be used to monitor maritime vessel traffic in any part of the world. In a previous tutorial, I demonstrated the use of software-defined radio, SDR, to monitor automatic dependent surveillance broadcast, ADS-B, messages to track aircraft. The transmission of these messages is now legally mandated in most parts of the world. The messages broadcast the aircraft's position, altitude, and speed. A similar concept is now available for marine vessels. The key difference is that it handles static, ship name and size, and voyage data, destination and draft, in addition to real-time position. Let us use a simple starter demonstration to collect data from marine vessels with a Python script. To track aircraft, I have, as previously shown in an older tutorial several years ago, something called PyAware. You may have heard of other systems like Flight Radar and so on, but I just use PyAware because it's a Houston-based company, and I've lived in Houston for almost about 45 years. So here are three receivers that are receiving data continuously and sending them back to the aggregation servers hosted by PyAware. So I can go ahead and look at the sky of what these aircraft are that I'm tracking. So my own antenna tracking these aircraft, and the color icons tell you the elevation. So some of the bigger dots you can see clearly are some of the higher elevations, 40,000 feet and above. And then the lower ones are the orange ones that are coming into land. So there are a couple of many airports around here. The most famous one, of course, is DFW, and then we have Addison, which is a very important general aviation. Then there's McKinney, and then there's the logistics one near Fort Worth, which is exclusively for freight traffic. So it gives you an idea that you can track planes in the air, and on the table here on the right-hand side, you can see the flight ident as well as the ICAO numbers that are assigned to them, and of course the parameters of the flight. So this is not meant to be an introduction or a tutorial on flight radar. The topic is marine vessel tracking. So I've given you the background. The concepts are almost the same in marine vessel tracking, but of course the data is less accurate because it's not available all the time. Naturally, the granddaddy of them all is the marinetraffic.com site, which of course has a public-facing free user interface. But if you want real-time data or you want to retrieve historical data, then you will have to shell out some dollars for the subscription access. But here I just want to show you the amount of traffic that is in the Strait of Hormuz that has been recorded because they're using satellite links. Unfortunately, we don't have the luxury of using that kind of expense, so I'll just illustrate the data for you, and then you can draw your own conclusion. So if we go in and look at the Strait of Hormuz in here, as I zero in, and you can see that it's relatively empty right now. There's very little traffic going on. There are some vessels that are going to UAE inbound and trying to enter the Persian or the Arabian Gulf, as you want to call it. And then there are some other vessels that are waiting to exit. So we don't see any Chinese vessels in here or Chinese origin vessels because they presumably have turned off their transponder. So as I explained to you, there is very little data that you can get out of this place here right now if you're using the AIS stream. But even with marine traffic subscription, you can see that you would get very little data. So I hope that gives you an idea that while you have access to the marine traffic data, it's only possible when the transponders are turned on. And marine vessels are notorious in turning off their transponders or providing misleading signals. It's unlike ADS-B for aircraft, where it is legally mandatory and, of course, very important to have that transmitted continuously while flying. Automatic identification system is split into performance tiers, Class A and Class B. Broadly stated, Class A is for ocean-going tankers and Class B is for intracoastal waterways. The data transmitted through AIS consists of static information, ship name, IMO number, call sign, length beam, and vessel type. Dynamic information, position, time, course over ground, speed over ground, and heading. And voyage related, draft, how deep is the ship in the water, hazardous cargo type, destination, and estimated time of arrival. Let's take a look at a very simple script to track data that is received by the AIS stream services. We have the classic async method for invoking this WebSocket in here. And once we get the responses, we just log it into the terminal window with the lat long and the vessel ID, which is the MMSI. So let's not worry too much about what is the MMSI, other than to say it's a unique identifier for a ship and the fact that we get lat long. Now I'm loading it through a config.toml file that I want to show you here. And basically what it requires is an API key from AIS stream. And then you can give the geofence a name and, most importantly, define the bounding box, the minimum and the maximum lat longs. And then to use it in future exercises to plot an HTML file, I've got some additional parameters that we'll use later. And notice that I'm using a vessel type of 8, which is tankers. So let's go ahead and run this and see what kind of output we get. So you can see right away that it does acknowledge reading the config.toml file, and it establishes a connection to the AIS stream through that async WebSocket call. And it's reported a single vessel with the ID here and the lat long, which is inside the bounding box. Now, the key thing to note here is that most of the ships in this area, in the Strait of Hormuz, are currently operating without their transponders. So as a result, very little data is going to be coming out, and so you will not see anything. I have another file for the Port of Houston that I can run, and I'll show you the output shortly. To run the script with another bounding box, it's best to again leverage a config.toml file. And I have one special called houston.toml here. And let me go pull it up. And you can see the bounding box in here for the Port of Houston. So we'll go ahead and run this and then look at the output. So when we run for the data to track vessels in the Port of Houston, we should get a lot more data than that for the Strait of Hormuz, simply because, the vessels have to have their AIS start turned on and they cannot be deceptive. So as you can see, immediately it gives us 5 vessels there and it gives us a summary. Then it finds 5 more vessels and gives us a summary. And you can see the MMSI for these are all unique. So I won't bore you with the details of the individual vessels themselves, but just scrolled all the way down to give you an idea of the volume of data that I could capture for the Port of Houston. And these are all tankers in the category of 8. So obviously, Port of Houston is an important port, and it collects a lot of AIS start data. So there are 150 vessels that are actively transmitting in the Port of Houston. And we can go ahead and update this map, as I'll show you shortly. In order to record the data on a file that I can display on a web server, I have created a slightly different variation of the Python script, and I collect historical data for about 45 seconds to get the data. Now again, this will not be very useful for the Strait of Hormuz right now, but using the data for the Port of Houston, you can see that I can start collecting data, and in 45 seconds, it is going to go ahead and log the data for me. So you can see from the output by the script that 125 vessels were recorded for the Port of Houston for the period of 3,600 seconds, which is roughly 1 hour. So let's go ahead and look at what we collected in the form of a visual map. So here's the output for the Port of Houston displayed on a world map. And as you can see, when I hover the mouse over the tags, I do see the correct MMSI corresponding for it. So this is the Galveston Bay, and inside out onto the left is the ship channel, and we end up with the Port of Houston right here. There are some barges and other smaller vessels on this side in here, and that's the Port Arthur refinery. So it's the intercoastal waterway along which some tankers may be passing through. So you can get a snapshot like this, or you can wait for a real-time interaction by using AIS Stream. This is really a very, very simple, quick and dirty demonstration to help you get started on looking up marine vessel movements. Here are some tips on adapting the starter code to track vessels. The Malaysian signal. Monitor vessels transiting the Malacca Strait. If they spend several days in the general area, then there is a high probability that the cargo is Iranian crude. MMSI ghosting. In these regions, vessels frequently turn off their transponders before reaching the terminal to evade sanctions. A historical snapshot script is essential to show where they were last seen before they went dark near the coast. We conclude that it is easy to track vessels, but there is a very big if. The vessels keep their transponders operating with correct credentials, understand that the data permits safer navigation. There are two types of data: land-based acquisition as sourced by AIS streams with obvious limitations from ship-to-shore communications, satellite-based monitoring like marine traffic for commercial applications. The API from all these sources appear to be very well documented with examples for multiple environments. Go ahead and try out the ones that you are most comfortable with. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. As we conclude, I want to take a moment to acknowledge the open source ecosystem that made this work possible. Our entire pipeline, from the mathematical filtering in Python to the final video edits you saw today, was built on the foundation of software freedom. Special thanks to the AIS team for access to the data without submitting credit card details, JetBrains PyCharm, used for Python script development, environment orchestration, and local debugging on Ubuntu desktop. I gratefully acknowledge the following core technologies that enabled our local first development and presentation. OBS Studio facilitated high fidelity screen capture and live demonstration of our AI auditing workflows. Kdenlive powered the nonlinear video editing required to prepare and sample our temporal action datasets. LibreOffice enabled the creation and design of visual presentation and documentation without proprietary constraints. Ubuntu provided the robust, high-performance Linux environment essential for our parallelized data processing and model inference. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.